Right now, the Atlantic Ocean isn't generating weather anymore. It's running an assembly line. 3 storms are queued up like planes on a runway, each one locked into the exact same flight path, aimed directly at Europe with no break window in between. This isn't chaos. This is synchronization. And meteorologists are starting to use a word they don't use lightly: unprecedented. Not because the storms are the strongest we've ever seen, but because they won't stop coming. Portugal just recorded wind gusts over 200 kilometers per hour. The UK just lived through its wettest January in 149 years. Cargo ships are sheltering in port, unable to navigate waves 3 stories tall. And the forecast? More. Back to back to back. The Polar Vortex has collapsed. The jet stream has locked in place. And Europe has become a target with no way out. In this video, we're going to show you exactly what happens when the atmosphere stops behaving like weather and starts behaving like a machine. Because if this conveyor belt doesn't break soon, we may not be watching storms anymore. We may be watching the birth of a new atmospheric rhythm. And it's already begun. Subscribe to follow this story to its conclusion, because what happens next in the Atlantic is only one chapter. The jet stream remains locked, the oscillation still synchronized, and the conveyor belt continues running toward an endpoint we can't yet predict. Europe braces, models recalculate, and somewhere over the open ocean, the next system is already forming. You'll want to know when it breaks. Right now, at this very moment, the Atlantic Ocean is doing something it's not supposed to do. It's not generating random weather. It's not cycling through storms in the chaotic, unpredictable way we've come to expect. Instead, it has become a factory, a relentless assembly line of destruction aimed directly at one continent, Europe. And the production schedule? Back to back to back, with no shutdown in sight. If you pull up the latest forecast models from Ventusky or the European Center for Medium-Range Weather Forecasts, you'll see something that makes meteorologists pause. 3 distinct low-pressure systems are queued up across the North Atlantic, like planes on a runway, each one following the exact same flight path. They're not scattered. They're not moving in different directions. They're locked into a single corridor, a storm highway carved through the atmosphere by a jet stream that refuses to budge, and every single one of them is pointed at Western Europe. This is not normal weather. This is what scientists call a coupled storm regime, a pattern where the atmosphere stops behaving like a random number generator and starts behaving like a machine. Storm after storm, pulse after pulse, forming along the same track, feeding off the same atmospheric fuel, striking the same coastlines before the previous damage has even been assessed. It's temporal clustering, and it means that the ground never dries, the rivers never recede, and the infrastructure never gets a chance to reset. Let me give you some context for what's already happened this winter. In January 2026, Storm Kristen slammed into Portugal with wind gusts exceeding 200 kilometers per hour. That's not just a bad storm. That's explosive cyclogenesis, a meteorological term for a system that intensifies so rapidly it behaves more like a bomb than a weather event. The storm didn't just knock down trees. It shredded roofs, flipped trucks, and left entire neighborhoods without power for days. Meanwhile, Northern Ireland and the United Kingdom recorded their wettest January in 149 years. That's not a typo. 149 years. We're talking about rainfall totals that break records set in the 1800s, back when we were still figuring out how to measure weather properly. Rivers overflowed. Farmland turned into lakes. Roads became rivers. And then, before the water could drain, the next storm arrived. Out in the Bay of Biscay, cargo ships were forced to shelter in port, unable to navigate waves reaching 8 to 10 meters. That's 3 stories tall, rolling walls of water that can snap a shipping container off its moorings and send it tumbling into the sea. Captains who have spent decades navigating these waters reported conditions they'd never seen before. Not stronger necessarily, but relentless. Wave after wave, system after system, with no break window. And here's the thing that keeps meteorologists up at night. The danger isn't just the intensity of any individual storm, it's the frequency. It's the fact that they keep coming. A single hurricane can devastate a coastline, sure, but then it moves on. The atmosphere resets. Communities rebuild. But when storms arrive in rapid succession, the damage compounds. Soil that's already saturated can't absorb more rain, so flooding worsens. Utilities that were damaged but holding on fail completely under the next gust. Emergency crews that were already stretched thin run out of supplies, out of time, out of people. So what's causing this? Why is the Atlantic locked into this mode? The answer lies in something called the North Atlantic Oscillation, or NAO. Think of it as a pressure seesaw between Iceland and the Azores. When the seesaw tilts one way, storms track north towards Scandinavia. When it tilts the other way, they dive south toward Europe. Right now, the NAO is in what's called a negative phase. And it's not just negative. It's deeply, persistently, stubbornly negative. And it's holding the storm corridor in place like a steel beam. Add to that a phenomenon known as Greenland blocking. A massive high-pressure system has parked itself between Greenland and Scandinavia, acting like a wall, a meteorological barrier that deflects storms southward instead of allowing them to escape northward into the Arctic. Normally, storms would curve up and dissipate over the cold northern seas. But this winter, they're hitting that wall and getting funneled straight into Europe, again and again and again. These aren't fringe theories. These are scientifically recognized teleconnections, large-scale atmospheric patterns that meteorologists track and forecast. The negative NAO phase is real. The Greenland blocking is real. The locked jet stream is real. What's unusual isn't that these patterns exist. It's that they're all aligned at the same time, and they're staying that way. So here's the question that's starting to ripple through the meteorological community. Is this just a bad season? A temporary cluster of unfortunate coincidences? Or is the atmosphere entering a new kind of mode? A locked state where the randomness we expect from weather gives way to something more synchronized, more rhythmic, more persistent. Because if this conveyor belt doesn't break soon, Europe may not be dealing with storms anymore. They may be dealing with a new atmospheric rhythm, one that doesn't stop when we expect it to. Let's talk about the jet stream. You've heard of it, probably seen it on weather maps, a wavy ribbon of wind snaking across the globe. But here's what most people don't realize. The jet stream isn't just a wind current. It's the steering river for every storm that forms in the mid-latitudes. Storms don't decide where to go. The jet stream decides for them. And right now, the jet stream isn't behaving like a freely flowing river. It's behaving like a canal, a locked pathway with walls on either side, and every storm that enters it gets funneled straight toward Europe. Normally, the jet stream oscillates. It waves north and south, looping and meandering like a snake trying to find the warmest path. Some storms get picked up and carried northeast toward Iceland. Others drift southeast toward the Mediterranean. It's chaotic, yes, but that chaos is what spreads the impact around. No single region gets hammered repeatedly because the storm track keeps shifting. But this winter, the jet stream has stopped oscillating. It's locked into what meteorologists call a semi-stationary waveguide, a fixed channel carved through the atmosphere by that massive, high-pressure system between Greenland and Scandinavia. That blocking high is acting like a dam, forcing the jet stream to bend around it. And when the jet stream bends, it doesn't bend gently. It dives sharply southward, dragging every developing storm with it. Here's the geometry of the trap. Imagine a storm forming off the coast of Newfoundland, as many Atlantic storms do. Normally, it would ride the jet stream northeast, passing between Iceland and Scotland before weakening over the cold Norwegian Sea. But this winter, as soon as that storm reaches the mid-Atlantic, it hits the wall. The Greenland blocking high deflects it southward, steering it toward Iberia, France, the United Kingdom. And because the jet stream is locked in place, the next storm follows the exact same path. And the next, and the next. This creates something meteorologists call increased residence time. Storms aren't just passing through Europe, they're lingering, because the usual escape routes have been closed off. Normally, a storm would race across the continent and dissipate over Scandinavia or Russia. But when the blocking pattern is this strong, storms slow down, they stall, they sit over the same regions for days, dumping rain, generating wind, eroding coastlines, flooding rivers. And here's where it gets worse. The storms arriving now aren't even particularly strong by historical standards. Some are moderate, some are barely classified as severe, but they're producing extreme impacts because the ground is already soaked, the trees are already weakened, the power grids are already strained. It's like punching someone who's already bruised. The first hit might not have been that bad, but the 10th, the 15th, that's when things break. Major meteorological agencies, including the UK Met Office and Météo France, have confirmed that this blocked regime is not speculation. It's observable fact. The jet stream is locked. The storm track is persistent. And the forecasts show no sign of a pattern break in the near term. That's the part that makes this so unusual. Blocking patterns happen all the time, but they usually last a week, maybe two. This one has been in place for over a month, and it's showing no signs of weakening. Now, let's add one more layer. When the jet stream elongates over warmer ocean waters, which it's doing right now, it increases the available energy for developing storm systems. The Atlantic has been running warmer than average this winter, which means there's more latent heat available for cyclones to tap into. It's like adding fuel to an already efficient engine. The storms aren't necessarily stronger, but they're forming more easily, more frequently, and they're maintaining their intensity longer because they're constantly being fed by warm, moist air from the ocean below. This isn't the first time we've seen this kind of clustering. In 1990, Europe experienced a winter storm series that caused billions in damage. In December 1999, 3 major storms, Anatol, Lothar, and Martin, struck in rapid succession, killing over 100 people and flattening entire forests. Meteorologists at the time described it as a once-in-a-generation event. But here's the thing. Once-in-a-generation events seem to be happening more often. Some researchers are now debating whether warming oceans are increasing jet stream waviness and persistence. The hypothesis goes like this. As the Arctic warms faster than the mid-latitudes, the temperature gradient that drives the jet stream weakens. A weaker jet stream becomes wavier, more prone to forming deep troughs and ridges that can lock in place. It's still a topic of active research, and there's no consensus yet, but the patterns we're seeing this winter align uncomfortably well with what the models predict. So why can't Europe escape? Because the geometry won't let them. The jet stream is trapped. The blocking high is holding, and every storm that forms is being funneled down the same corridor. But here's the unsettling part. The real driver of this pattern might not be at the surface. It might not even be in the troposphere, where weather happens. It might be high above in the stratosphere, where the polar vortex has been quietly falling apart. In early 2026, something happened in the stratosphere that most people never heard about. The polar vortex split. Not a little wobble. Not a temporary disturbance. A full-blown, sudden stratospheric warming event. The kind that meteorologists track carefully, because it tends to have consequences down here at the surface, weeks or even months later. And those consequences are starting to show up now, in the form of a storm track that's been completely rewired, Most people think of the polar vortex as something that sends cold air south, and that's true. But that's only half the story. The polar vortex is a massive circulation of winds in the stratosphere, spinning around the Arctic like a contained whirlpool. When it's strong and stable, it keeps the jet stream relatively tight and predictable. But when it weakens or splits, it doesn't just release cold air. It changes the shape and speed of the jet stream itself. It alters the entire atmospheric circulation pattern across the northern hemisphere. Here's what happened. In late January, temperatures in the stratosphere over the Arctic spiked by more than 50 degrees Celsius in just a few days. That's not a typo. 50 degrees. The polar vortex, which is normally one of the coldest places on Earth, suddenly became warmer than parts of the continental United States. And when that happens, the vortex weakens, splits, or in some cases, completely collapses. The warming itself happens in the stratosphere, about 30 to 50 kilometers above the surface, far above where weather occurs. But the effects don't stay up there. Over the following weeks, the disruption propagates downward, a phenomenon called downward propagation, and it starts to influence the troposphere, the layer where we live, where storms form, where the jet stream flows. And what it does is amplify the meridional temperature gradient, the north-south temperature difference that fuels storm development. Think of it this way. Storms in the mid-latitudes, the kind hitting Europe right now, are powered by temperature contrasts. Warm air from the south meets cold air from the north, and the atmosphere tries to smooth out the difference by generating wind and precipitation. The bigger the temperature contrast, the more energy available for storms. And when the polar vortex splits, it doesn't just send cold air south. It enhances that contrast, cranking up the baroclinic instability that fuels cyclones. But here's where it gets interesting. Models predicted the sudden stratospheric warming event. They saw it coming. What they didn't predict was how strongly it would interact with the negative NAO phase that was already in place. It's like two gears meshing together in a way that amplifies the output. The SSW event shifted the jet stream, yes, but the negative NAO locked it in place. And once storms started forming along that locked jet stream, they reinforced the pattern rather than breaking it. This is nonlinear feedback, and it's one of the hardest things to predict in atmospheric science. Normally, weather systems are chaotic. One storm might strengthen the jet stream in one place, weaken it in another, and the whole pattern shifts within days. But when multiple large-scale drivers align, the polar vortex disruption, the NAO phase, the Greenland blocking, the system can enter a feedback loop where each storm helps maintain the pattern that created it. It's self-reinforcing. And it's exactly what appears to be happening right now. Past winters have shown that SSW events often precede stormy European seasons. 2018, for example, saw a similar vortex disruption, followed by weeks of cold, snowy weather across Europe. But this season's persistence is unusual. Normally, the atmospheric response to an SSW event lasts 2 to 4 weeks. We're now well beyond that window, and the storm conveyor belt is still running. So here's the question meteorologists are grappling with. If the polar vortex collapse helped shift the storm track, why did the storm shift so far south? Because normally, when the vortex weakens, storms track northeast towards Scandinavia and Russia, following the cold air. But this winter, they're diving southeast, hammering Iberia, a region that's usually too far south to catch the brunt of North Atlantic cyclones. Something else is going on. Something that's steering storms into a part of the Atlantic that doesn't usually see this kind of activity. And that brings us to one of the strangest mysteries of this winter. Why has Iberia become the front line? Spain and Portugal are not used to this. The Iberian Peninsula sits at the southern edge of Europe, a region that typically enjoys mild winters with occasional rain, but rarely the full fury of North Atlantic cyclones. Storms usually track north, toward the British Isles, France, the North Sea. Iberia gets the tail end, The weakening remnants, not the direct hits. But this winter, everything has flipped. Storm after storm is making landfall at unusually southern latitudes, and meteorologists are trying to figure out why. Let me paint the picture. In early January, Storm Kristen tore across northern Portugal with winds exceeding 200 kilometers per hour. That's stronger than many hurricanes. Trees were ripped from the ground. Buildings lost roofs. Power lines snapped like strings. And then, just days later, another system followed the same path. And then another. It's not just that Iberia is getting hit. It's that Iberia has become the primary target, the bullseye in a pattern that doesn't align with historical norms. The usual storm track for the North Atlantic runs northeast, from Newfoundland toward Iceland, then on to Scandinavia. There's a secondary track that dips slightly south toward the British Isles, but it rarely extends as far south as Portugal or Spain. Yet this winter, the storms are diving southeast in a way that forecasters find difficult to explain using the standard atmospheric mechanisms alone. Part of the answer lies in that Greenland blocking high we talked about earlier. It's not just deflecting storms southward, it's deflecting them sharply southward, forcing the jet stream to bend at an angle that sends systems directly toward the Iberian coast. But blocking alone doesn't fully explain the persistence. There's something else feeding the pattern, and it's coming from the ocean itself. The subtropical Atlantic has been running warmer than average this winter, particularly in the region off the coast of Northwest Africa and the Canary Islands. Warmer ocean waters mean more latent heat, more moisture, more fuel for storms. And when a developing cyclone passes over these warm waters, it doesn't just maintain its strength, it can actually intensify, even at latitudes where storms typically begin to weaken. It's like a second wind, a recharge station that keeps the storm engine running longer than it should. There's also something called the Madden-Julian Oscillation, or MJO, a wave of enhanced tropical convection that moves slowly eastward around the equator. When the MJO is in certain phases, it can influence mid-latitude weather patterns by triggering atmospheric waves that propagate poleward. This winter, the MJO has been unusually active, and some researchers think it may be amplifying the jet stream pattern over the Atlantic, making the troughs deeper and the ridges higher. It's a complex interaction, one that's still being studied, but the timing lines up. What we're seeing might be something called storm track bifurcation collapse. Normally, there are two main storm tracks in the North Atlantic, a northern one toward Iceland and a southern one toward the Mediterranean. They're distinct, separate corridors, but when the atmospheric conditions align just right, those two tracks can merge into a single dominant pathway. And right now, that pathway runs straight through Iberia. Historical analogs are hard to find. There are years where southern Europe saw increased storm activity, winters where blocking patterns steered systems south. But this level of persistence, this repetitive hammering of the same coastlines, is exceptional. And here's the part that's making forecasters uneasy. Models suggested that the blocking pattern would relax by mid-February. We're past that point now. And the forecasts still show multiple storms lining up, aimed at the same targets. So here's the speculative question that's starting to circulate in the research community. Could there be a feedback loop between the repeated storms and the ocean heat flux that's helping to maintain the corridor? Here's the idea. When storms repeatedly pass over the same region of warm ocean water, they don't just extract heat, they also churn up the upper layers, mixing warmer water with cooler water below. But if the ocean is warm enough deep down, that mixing doesn't cool the surface. It keeps it warm, and that warmth continues to feed the next storm, and the next. It's a feedback loop, ocean to atmosphere to ocean, that could theoretically sustain a storm corridor longer than models would predict. There's no proof yet. It's a hypothesis, a possibility being explored in research papers and conference presentations. But the fact that it's being discussed at all tells you something. The atmospheric community is looking for explanations because the standard mechanisms, the ones we understand well, don't fully account for what we're seeing. And when multiple oscillations align at once, when the NAO goes negative, when the polar vortex splits, when the MJO amplifies, when the ocean runs warm, the atmosphere stops behaving like weather. It starts behaving like a synchronized system, and that's when things get unpredictable. Let's address the elephant in the room. Is this natural variability, or is something else going on? Because that's the question everyone's asking, even if they're not saying it out loud. Is this just a bad winter, the kind that happens once every few decades? Or is this an emerging signal of something new, something tied to the broader changes happening across the planet? Mainstream meteorology has a clear answer. This pattern is the result of known drivers: the negative NAO phase, the sudden stratospheric warming event, teleconnections from La Niña in the Pacific, and warmer than average Atlantic waters. All of these are well-documented phenomena, pieces of the climate system that we've observed and studied for decades. And when they align in a certain way, you get winters like this: stormy, persistent, destructive. It's rare, but it's not unprecedented. It's weather. But there's a growing debate, particularly among researchers studying climate dynamics, about whether the frequency and persistence of these patterns are changing. The hypothesis goes like this: as the planet warms, the Arctic warms faster than the mid-latitudes, reducing the temperature gradient that drives the jet stream. A weaker jet stream becomes wavier, more prone to forming deep ridges and troughs that can lock in place for extended periods. And when the jet stream locks, weather patterns persist. Droughts last longer, heat waves last longer, and yes, storm corridors last longer. This is an active area of research, and there's no scientific consensus yet. Some studies show a link between Arctic amplification and jet stream persistence. Others find no significant trend. The data is noisy, the timescales are long, and the atmosphere is complex. But the patterns we're seeing this winter, the locked jet stream, the persistent blocking, the repeated storms, they align uncomfortably well with what some models predict for a warming world. Now, let's talk about the fringe speculation, because it's out there, circulating online, and it needs to be addressed. Some people are pointing to solar activity, claiming that changes in the sun's output are influencing atmospheric circulation. Others are suggesting that ionospheric heating programs, experiments that send radio waves into the upper atmosphere, are altering jet stream dynamics. And I'm going to say this clearly: there is no credible scientific evidence linking artificial causes to the storm pattern we're seeing right now. None. That said, there is legitimate research on solar-stratosphere interactions. The sun's activity does influence the stratosphere, and changes in the stratosphere can, in turn, influence the troposphere. It's a real connection, but the effects are subtle, far too small to drive the kind of persistent storm corridor we're witnessing. The sun isn't causing this. The atmosphere is causing this, driven by processes we understand reasonably well, even if we can't predict them perfectly. But here's where things get interesting, and this is where speculation meets science in a way that's worth exploring. The idea of atmospheric resonance. Think of it like this: the atmosphere has multiple oscillations: the NAO, the MJO, the polar vortex dynamics, each operating on different timescales. Most of the time, they're out of sync. One oscillation is in a positive phase, while another is negative. They cancel each other out, or at least dampen each other's effects. But occasionally, rarely, they synchronize. They align. And when that happens, their effects amplify. It's not a new concept. Physicists have studied resonance for centuries. When two pendulums swing at the same frequency, they can lock together, reinforcing each other's motion. When an opera singer hits the right frequency, a wine glass shatters. The atmosphere isn't a pendulum or a wine glass, but it's a non-linear system, And nonlinear systems can exhibit resonance-like behavior when multiple forcing mechanisms align. Historical winters have shown this kind of synchronization before. The winter of 1963, for example, saw a combination of blocking patterns, vortex disruptions, and ocean anomalies that produced one of the coldest, stormiest winters in European history. It lasted months, and then it broke. The oscillations fell out of sync, the patterns shifted, and the atmosphere returned to its usual chaotic self. So here's the unresolved mystery. Why did all these amplifying teleconnections align in the same winter season? Is it random chance, the atmospheric equivalent of rolling snake eyes 5 times in a row? Or is there some underlying mechanism, some feedback or interaction we don't fully understand, that causes these oscillations to synchronize more often under certain conditions? Nobody knows yet. But if this is resonance rather than coincidence, if the oscillations are temporarily locked together, then the storms may continue until one major oscillation shifts phase. The NAO could flip positive. The polar vortex could recover. The MJO could enter a different phase. Any one of those changes could break the pattern. But until then, the conveyor belt keeps running, and Europe keeps getting hit. Which brings us to a larger question. What happens when we start seeing these kinds of persistent patterns, not just in weather, but in other areas of science? Because that's exactly what's happening. Let's shift gears for a moment, because while Europe is bracing for the next storm, something equally significant is happening inside the world of weather forecasting. Artificial intelligence is starting to beat the traditional physics-based models that have dominated meteorology for decades, and the implications go far beyond just predicting rain or wind. We're talking about a fundamental shift in how we understand and anticipate complex atmospheric behavior. We're talking about machines that can see patterns in chaos that human-designed equations cannot. And we're talking about a future where the question isn't just what the weather will be, but whether we can trust a system we don't fully understand to tell us. Traditional weather models work like this. You take the laws of physics, fluid dynamics, thermodynamics, radiation transfer, and you encode them into massive computer simulations. You feed in the current state of the atmosphere, temperature, pressure, humidity, wind speed at millions of points around the globe, and then you let the simulation run forward in time, solving equations at every step. It's brute force calculation, and it works remarkably well, but it has limits. These models are built on centuries of scientific understanding, from Newton's laws of motion to the Navier-Stokes equations that govern fluid flow. They represent our best attempt to capture reality in mathematical form, to predict the future by solving the present. The problem is that the atmosphere is nonlinear. Small changes in initial conditions can lead to wildly different outcomes. The famous butterfly effect that Edward Lorenz discovered in the 1960s, when he realized that rounding a single decimal place in a weather simulation could completely change the forecast. And while physics-based models can capture the general flow, the large-scale patterns, the movement of high and low pressure systems, they struggle with the messy details, the interactions between scales, the feedback loops, the chaotic triggers that can cause a storm to suddenly intensify, or a blocking pattern to persist longer than expected. They're solving approximations of approximations, and at some point, the errors compound. There's also a computational limit. To perfectly simulate the atmosphere, you'd need to model every molecule, every turbulent eddy, every cloud droplet. That's impossible. So instead, models divide the atmosphere into grid boxes, each one representing a chunk of space, maybe 10 kilometers on a side. Everything happening inside that box gets averaged, smoothed out, parameterized. And that works for large-scale features, but it means you're missing the small-scale processes that can trigger big changes. A model might know there's going to be a storm, but it can't always tell you if that storm will explosively intensify or fizzle out. Enter artificial intelligence. AI doesn't solve physics equations. It learns from data. You train a neural network on decades of past weather observations, showing it what the atmosphere looked like at time zero, and what it looked like 6 hours later, 12 hours later, 24 hours later. And after seeing enough examples, millions of them, the AI starts to recognize patterns. Not the physics, not the equations, but the statistical relationships, the subtle connections between temperature gradients and storm formation, between jet stream shapes and blocking persistence, between ocean temperatures and cyclone intensification. It's pattern recognition at a scale and complexity that no human could replicate. Think of it like teaching a child to recognize faces. You don't explain the geometry of noses or the physics of light reflecting off skin. You just show them thousands of faces, and eventually they learn. They can identify a face in a crowd, even if they've never seen that particular person before, because they've learned the underlying patterns. AI does the same thing with weather, except instead of faces, it's learning pressure fields, temperature gradients, wind vectors, moisture content, all evolving in four-dimensional space-time. And here's the remarkable part. In recent tests, AI-based forecasting systems have shown improved skill in predicting cyclone genesis and blocking persistence compared to traditional models. They're not better at everything. Physics-based models still dominate at short-range forecasts, the next 24 to 48 hours, where the initial conditions matter most, and the atmosphere hasn't had time to diverge into chaos. But for medium-range forecasts, 3 to 10 days out, AI is starting to edge ahead, particularly for complex, nonlinear events like rapid intensification or pattern transitions. The kind of events that matter most for emergency planning, for evacuation decisions, for life and death scenarios. The reason is simple. AI can detect hidden pattern relationships that are difficult to represent in physics equations. It's not that the physics is wrong. It's that the real atmosphere has so many interacting processes: turbulence, convection, cloud microphysics, ocean coupling, land surface feedbacks, aerosol effects, that fully capturing them in a model is computationally impossible. Even if you had all the computing power in the world, you'd still be limited by our incomplete understanding of how some of these processes work. AI sidesteps that problem by learning the effective relationships directly from observations. It doesn't need to know why a certain pattern leads to rapid intensification. It just needs to recognize that it does. Now here's the speculative question. Could AI-based systems have predicted the persistence of the Atlantic storm conveyor belt earlier than traditional seasonal models? Because seasonal forecasts, the ones that try to predict weather patterns months in advance, have struggled this winter. Most seasonal models suggested that the blocking pattern would break by early February. It didn't. They underestimated the persistence. They missed the synchronization. But an AI system, trained on past examples of synchronized oscillations and locked jet streams, might have recognized the pattern earlier, flagged it as unusual, and extended the forecast window. It might have seen something in the data that the physics-based models couldn't capture. We don't know yet. This is cutting-edge research, experiments being run in real time as the winter unfolds. Some AI systems are being tested in parallel with traditional forecasts, their predictions logged but not officially issued, so researchers can compare performance after the fact. And the early results are intriguing. In some cases, the AI caught the persistent signal days earlier than the traditional models. In other cases, it overestimated the intensity, but nailed the timing. It's not perfect, but it's learning. But the implications for early warning systems and disaster preparedness are enormous. If we can identify clustering events weeks ahead, if we can say with confidence that Europe is about to enter a month-long storm siege, then governments can pre-position resources, reinforce infrastructure, evacuate vulnerable areas. we can save lives. Emergency managers could stock supplies, stage rescue equipment, prepare shelters, all before the first storm even arrives. Instead of reacting to each storm individually, scrambling to respond, we could treat the entire sequence as a single event and prepare accordingly. But there's a catch. AI models are black boxes. They work, but we don't always know why they work. A physics-based model can tell you that a storm will form because there's a temperature gradient and wind shear, because the baroclinic instability has reached a critical threshold, because the jet stream is providing favorable upper-level divergence. You can trace the reasoning step by step, equation by equation. An AI model just says, based on the data, a storm will form here. And if it's wrong, if it makes a prediction that doesn't pan out, we can't always trace back the reasoning to figure out what went wrong. The neural network has millions of parameters, billions of connections, and understanding exactly which combination of inputs led to which output is extraordinarily difficult. That makes meteorologists nervous, and rightfully so. You don't want to issue an emergency warning based on a system you don't fully understand. You don't want to evacuate a city because an algorithm said so, only to have nothing happen. Trust is earned through transparency, and AI, by its nature, is opaque. It's a trade-off. You gain predictive power, but you lose interpretability. And in fields where lives are at stake, interpretability matters. So the current approach is hybrid. Use AI to complement physics-based models, not replace them. Let the AI highlight patterns and anomalies that traditional models might miss, then use the physics to validate and interpret. If both systems agree, you have high confidence. If they disagree, you dig deeper, figure out why, use human judgment to weigh the evidence. It's a partnership, and it's already changing how forecasts are made at major meteorological centers around the world. The European Centre for Medium-Range Weather Forecasts, the UK Met Office, the National Oceanic and Atmospheric Administration in the United States. They're all experimenting with AI-assisted forecasting. But here's the bigger picture. We may be entering an era where the atmosphere's nonlinear behavior becomes more predictable through pattern recognition than through physics alone. That's a profound shift. It suggests that some aspects of weather, particularly the complex multi-scale interactions that drive persistent regimes, are better understood statistically than mechanistically. We may never fully solve the equations, never completely capture every feedback loop and interaction in a perfect mathematical model, but we can learn to recognize the fingerprints, the signatures, the telltale signs that a pattern is forming, that oscillations are synchronizing, that the atmosphere is about to lock into a persistent mode. It's like the difference between understanding how a language works grammatically and being able to speak it fluently. You can study grammar rules for years and still struggle to form a sentence. Or you can immerse yourself in the language, hear it spoken thousands of times, and develop an intuitive feel for what sounds right. AI is doing the latter with weather. It's developing fluency without necessarily understanding the grammar. And here's the unsettling part. If AI can predict persistent instability in the atmosphere, if it can flag when multiple oscillations are about to synchronize, then we might start seeing similar tools applied to other complex systems. Financial markets, ecosystems, power grids. Anywhere you have nonlinear interactions and feedback loops, you have the potential for pattern recognition to outperform traditional analysis. Stock market crashes often come with warning signs, subtle shifts in trading patterns that only become obvious in hindsight. What if an AI could recognize those patterns in real time? Ecosystem collapses, the sudden die-off of a coral reef, or the abrupt shift from forest to grassland often follow similar nonlinear dynamics. What if we could predict those transitions before they happen? Power grids are particularly vulnerable. They're complex networks with thousands of nodes, and when one part fails, it can cascade, triggering failures elsewhere, leading to blackouts. It happened in 2003 when a tree branch touched a power line in Ohio and triggered a cascading failure that left 50 million people without electricity. Engineers have been trying to predict and prevent these cascades for decades using traditional network models. But what if an AI trained on the patterns of past failures could recognize the early warning signs, the subtle imbalances that precede a collapse? The possibilities are vast, and so are the risks. Because these systems, financial markets, ecosystems, power grids, they're all connected to human welfare. Get the prediction wrong, and people suffer. Trust the AI too much, and you might miss something the physics would have caught. Trust it too little, and you miss the warning. It's a balance we're still learning to strike. And that brings us to the final piece of the puzzle. Because the atmosphere isn't the only system showing signs of persistent instability right now. Across multiple fields, across multiple scales, scientists are observing systems that refuse to behave the way we expect. Systems that lock, systems that persist, systems that synchronize. And the question we're all starting to ask is whether these are isolated incidents, or whether we're seeing something deeper, something fundamental about how complex systems behave when they're pushed to their limits. Here's where things get strange. Or maybe not strange, maybe revealing. Because while meteorologists are watching the Atlantic lock into a storm conveyor belt, scientists in completely unrelated fields are observing something similar. Systems that normally fluctuate, that oscillate smoothly between states, are instead locking into persistent regimes, holding patterns that last longer than expected, behaving in ways that suggest synchronization rather than randomness. And the timing is what makes this interesting. It's happening now, across multiple disciplines, as if the universe is running the same experiment in different laboratories and getting the same result. Take fusion research. For decades, scientists have been trying to confine plasma, superheated ionized gas, long enough to sustain a fusion reaction. The challenge is stability. Plasma is turbulent. It wants to escape. Heat it to 100 million degrees, the temperature needed for fusion, and it becomes a roiling mass of charged particles that will find any weakness in the magnetic field containing it and break free. And most attempts to confine it result in oscillatory instabilities, waves and fluctuations that eventually cause the plasma to break apart. The plasma doesn't just sit there. It writhes. It oscillates. And those oscillations grow until the confinement fails. But recently, researchers have achieved longer confinement times by carefully controlling those oscillations, guiding them into quasi-stable states where the turbulence doesn't dissipate, but instead settles into a persistent rhythm. It's not equilibrium, it's sustained instability. The plasma is still oscillating, still turbulent, but the oscillations have synchronized into a pattern that doesn't destroy the confinement. It's like taming a wild animal by learning its rhythm, by moving with it instead of against it. And it works. Confinement times have increased. Fusion reactions have lasted longer. And the key insight is that stability doesn't mean stillness. It means controlled oscillation. This is counterintuitive. For years, fusion scientists tried to eliminate the oscillations, to create perfectly smooth, stable plasma. But the plasma wouldn't cooperate. It wanted to oscillate. So instead of fighting it, researchers started working with it, shaping the magnetic fields to guide the oscillations into patterns that wouldn't tear the plasma apart. And it turns out that a plasma in sustained, synchronized oscillation can be more stable than a plasma that's artificially forced into stillness. The oscillations dissipate energy in a controlled way, preventing larger, more destructive instabilities from forming. Now look at exoplanet climate modeling. Astronomers studying tidally locked planets, worlds where one side always faces their star, have discovered that these planets can develop permanent jet streams, atmospheric rivers that never shift, locked in place by the planet's rotation and the constant heating on one side. These are planets where one hemisphere is eternally day, baking under starlight, while the other is eternally night, frozen in darkness. And the temperature contrast between the two sides creates a permanent atmospheric circulation pattern, a jet stream that forms once and then never moves. And those jet streams create permanent storm corridors, regions where cyclones form continuously, fed by the temperature contrast between the day side and night side. It's a planetary scale conveyor belt, and it doesn't stop. Ever. New storms form. Old storms dissipate. But the corridor itself, the pathway, the pattern, it's permanent. As long as the planet remains tidally locked, as long as one side faces the star, the storm corridor persists. It's not weather anymore. It's climate. It's a permanent feature of the planet's atmospheric structure. What's striking is that these exoplanets aren't rare. We've found hundreds of them, and many show signs of these locked circulation patterns. Planets orbiting red dwarf stars are particularly prone to tidal locking because they orbit so close to their dim stars that gravitational forces freeze their rotation. And when astronomers model the atmospheres of these worlds, they find the same thing again and again. Permanent jet streams, permanent storm corridors, atmospheric patterns that form once and persist indefinitely, not because they're in equilibrium, but because the forcing mechanisms never change. Back here on Earth, climate modelers are studying atmosphere-ocean coupling thresholds, the points at which feedback loops between the ocean and atmosphere can flip abruptly once certain conditions align. The idea is that complex systems can behave normally for years, oscillating smoothly, and then suddenly lock into a new mode when multiple forcing mechanisms synchronize. It's not a gradual transition, it's a phase shift. 1 year, you're in normal variability. The next, you're in a persistent regime, and you stay there until something breaks the synchronization. The most famous example is El Niño, a climate pattern in the Pacific Ocean that oscillates between warm and cool phases every few years. Normally, the transitions are predictable. The ocean warms, triggers atmospheric changes, then cools again. But occasionally, El Niño events become unusually persistent, lasting longer than expected, resisting the mechanisms that normally would flip them back to neutral. And when that happens, the impacts compound. Droughts last longer, floods persist, weather patterns that should shift stay locked in place. Researchers studying these persistent El Niño events have found that they often occur when multiple climate oscillations synchronize. The Pacific Decadal Oscillation aligns with the El Niño cycle. The Indian Ocean dipole enters a particular phase. The Madden-Julian Oscillation amplifies at just the right time. And when all these oscillations line up, when they reinforce each other instead of canceling out, the system locks. It enters a persistent mode that resists change, that maintains itself through feedback loops, that only breaks when one of the underlying oscillations finally shifts out of phase. This is the language of nonlinear dynamics, a branch of mathematics and physics that studies systems where small changes can have large effects, where feedback loops can amplify or dampen behavior, where multiple oscillations can synchronize and lock together. It's the science of complexity, and it applies to everything from pendulums to plasmas to planetary atmospheres. It's the same mathematics that describes why your heart beats in rhythm, why fireflies in a forest flash in unison, why bridges can collapse when soldiers march in step, their footfalls resonating with the bridge's natural frequency. Synchronization is everywhere in nature. It's not the exception, it's the rule. And once you start looking for it, you see it in systems you never expected. Neurons in the brain fire in synchronized waves. Chemical reactions oscillate in lockstep, creating patterns that pulse and spiral. Even galaxies, spiral galaxies like our own Milky Way, maintain their spiral arms through synchronized oscillations of stars orbiting the galactic center. The arms aren't fixed structures. They're density waves, patterns that persist even as individual stars move through them, entering and leaving the spiral over millions of years. So here's the analogy. What if the Atlantic storm siege isn't just a weather event? What if it's an example of synchronized oscillations in Earth's atmosphere, a real-world demonstration of how complex planetary systems behave when multiple forces align at once? The NAO oscillation, the polar vortex dynamics, the MJO, the ocean heat anomalies, they're all oscillating systems. Each one has its own natural frequency, its own timescale, and most of the time, they're out of sync. The NAO is positive, while the MJO is in a neutral phase. The polar vortex is strong, while the ocean is cool. They cancel each other out, or at least they don't reinforce. But when they oscillate in phase, when they synchronize, they can produce extreme but temporary patterns that persist far longer than any individual component would suggest. It's like pushing a child on a swing. One push doesn't do much, but if you push in rhythm with the swing's natural motion, in phase with its oscillation, each push adds energy. The swing goes higher, the oscillation amplifies. And that's what may be happening in the atmosphere right now. Multiple oscillations, each one relatively weak on its own, aligning in phase and amplifying each other, creating a persistent pattern that none of them could create alone. It's speculative. I want to be clear about that. This interpretation is hypothetical, not yet verified by rigorous analysis. There are no peer-reviewed papers that definitively prove the Atlantic storm corridor is the result of synchronized oscillations. But it's actively discussed in climate dynamics research, and the parallels with other fields are hard to ignore. Fusion plasmas lock into stable oscillations. Tidally locked exoplanets develop permanent storm corridors. Earth's atmosphere, caught between multiple synchronized oscillations, generates a persistent storm conveyor belt. The mechanisms are different, but the underlying behavior, the locking, the persistence, the synchronization, it's the same. And if that's true, if we're witnessing a temporary synchronization rather than a permanent change, then the storms will eventually stop. The oscillations will fall out of phase. The NAO will flip positive, weakening the storm track. The polar vortex will recover its strength, changing the jet stream pattern. The MJO will shift into a different phase, reducing the amplification. The ocean will cool, cutting off the energy supply. And the atmosphere will return to its usual chaotic self, generating storms randomly rather than systematically. The synchronization will break, the way it always does, because nothing in nature stays perfectly in phase forever. But until then, Europe is locked in, the conveyor belt is running, and 3 more storms are lined up, following the same track, striking the same coastlines, compounding the same damage. The question isn't whether it will end. It will. The question is when and how much damage will accumulate before the pattern breaks. So what does this mean for us? It means we need to start thinking about weather differently. Not as isolated events, but as patterns. Not as random fluctuations, but as synchronized oscillations that can lock together, amplify, and persist. It means we need better tools to predict when these synchronizations are forming, and AI might be part of the answer. Pattern recognition algorithms that can spot the early warning signs that multiple oscillations are coming into phase. And it means we need to prepare for a world where extreme but temporary patterns become more common. Not because the climate is changing in a linear way, but because the climate is a nonlinear system. And nonlinear systems do things like this. They lock, they persist, and then they break. The Atlantic storm siege may be more than just a stormy winter. It may be a real-world demonstration of how complex planetary systems behave when multiple forces synchronize at once, producing extreme but temporary patterns that challenge our expectations, strain our infrastructure, and force us to rethink what we mean by normal. Because normal in a nonlinear system isn't a single state. It's a range of states, including rare but natural periods of synchronization, where the system locks into patterns that persist far longer than we expect. The ocean isn't out of control. It's locked in, and that might be even more unsettling, because locked systems eventually unlock. And when they do, when the oscillations fall out of phase and the pattern breaks, we have no way of knowing what comes next. We only know that it will be different. And the transition, the moment of breaking, can be just as extreme as the locked state itself.